All right, so let's finish the lecture 6. We were at the end of lasso. Just to review a bit. Yeah, I really like this, so I abandoned my pointer and used the physical pointer. So this is a lasso we talked about. So like this is the diamond shape. Your parameter needs to stay inside, and then at the same time, you want to minimize the loss function. That loss function is the sum of squared regression area, and you have to think about there's a kind of a bell shape because that's the SSE loss function really look like. And then that bell shape and this kind of, this shape will intersect highly likely in the corner. Just think about there's a bell, there's some kind of cylinder with the corners. Of course, the corner is more likely to touch that point, right? Rather than this part touch that point. So that's intuitive reason, but actually there are theoretical reasons why a lot of the corner points means those vectors and with a lot of entries as zeros. Those are the corner points. Like in this case, is beta 2 is 0, and beta 1, beta 1 is 0, beta 2 has some kind of values there. So we said, lasso is so great. It has this automatic feature selection functions, and we really like that because it gives you simpler models, like faster computation, hopefully in the operational phase. And then we compare the ridge regression versus the lasso, and you can actually tell very easily lasso is the corner point. Ridge regression has it's not necessarily the corner point because it's a rounded circle shape, and so but it has this function of shrinking the beta, which essentially make the beta smaller. And we actually proved that shrinking is related to the lambda. The larger the lambda, the more shrinkage you apply on the beta vector. The essentially lasso versus the ridge regression, it just replaced L1 norm. So this is, hopefully you remember what is L1 norm. It's just a summation of absolute values of each entry, and it replaced that L2 norm, which is the quadratic of each entry, then take the summation. So this is actually L2 norm's quadratic, because L2 norm, the definition has a square root on top of this. It's performing implicit feature selection and make hopefully easier to understand models, and the computation will hopefully more, actually it will be more efficient because there are less features to compute. So we covered all this, and then there's a small error, and some student pointed out, I really thank you. So this is actually n, so if you have n prime test data, your operational cost is O(n prime) times p, because this is how you use the regression model, right? This is how you implement it in your homework 1, is that test data, if you put it as a matrix form, it's this matrix times beta learned, just the learned beta parameter. I should actually put star there because this is the learned, the beta star, and this operation costs O(n prime) times p, and 1 OP prime. When you have smaller p, of course, this is more computationally efficient. And also storage-wise, if you think about it, so this is n times p prime, right? And when you have less features, it's apparently you don't need to save all the features at all in the operational phase, right? Because it's just not useful at all. I can only just extract and save the p prime features instead of the p features. Question about this? All right, so now let's move to something, it's a combination of regression and lasso called elastic net. So there's issues as I pointed out for lasso. Lasso, yes, it does the shrinkage and the variable selection. However, lasso can select at most n variables before it saturates. So it mostly applied in the situations p larger n, right? So even if you have more than n features are important, and lasso, the whole formulation of lasso just avoids to select more features. And the other very important drawback of lasso is if you have correlated features, so let's just think extreme of correlated features is one feature assuming during the operation or generation got repeated 3 times. It's very likely, right? Maybe you have errors in the feature selection, that one feature got repeated 3 times. And also, it just doesn't know which one to pick, and it will pick randomly one of those. And it will assign maybe x1, x2, x3, and so this is an extreme case, right? So maybe pick x2 and assigning x1 and x3 as 0 weight. If you think about a domain expert look at this answer, it will be really concerning. And the reason why this is the case, I have explanations in the extra slides, is because when you have correlated features and the solution of lasso becomes non-strong convex. There's no global solution in that case. If this is too much, don't worry about it, but if you're interested in understanding why, read the extra slides. And there's also the Element of Statistical Learning book explains this very well. So I put the book chapter of that book chapter in the to-read sections of our calendar, the schedules. Feel free to read that whole chapter explaining, discussing about this too. All right, so the ElasticNet is really just a combination of L1 and L2. So L1 part is the lasso used by lasso. It generates sparse models. It generates sparse model. And L2, it's adding this L2 penalty is, so there's a little bit like benefits why it's encourage grouping effects. So what I meant grouping is if there is a group of features are very correlated, and it will assign, the elastic net will assign similar weights to the whole group. And which, if you think about it, this is exactly solve the issue of lasso. It's also stabilized the L1 regularization path. This is a little bit hard, and we're going to talk about what do we mean regularization path after the elastic net. And also it remove this n, the size of the number of features to be selected. Elastic net can select more than n features, when p larger than n. Okay, so what is elastic net? It's a very easy formulation. It's really just lambda 2, L2 norm, plus lambda 1, L1 norm. And lambda 1 and lambda 2 are larger than 0, and you have to select it. So, so there are actually a lot of different variations of elastic net. And what we show here is something called a naive elastic net. And it's totally equivalent to this form we actually discussed, right? In the ridge regression, you can either have this one objective function with the sum of squared error plus this part, when we call Lagrangian terms, considering the regularization, or you just reformulate it as minimize the sum of squared error, and at the same time subject to a constraint. In the L1 case is the diamond or the simplex in the high dimensional case. In the L2 case is the circle or the sphere in the high dimensional case. And then the elastic net is really just this combination of L1 and L2 if you assume, if you assume alpha equals to, so I'm just reformulating. This reformulation is assuming alpha is 0.2, 0.5, and this is 0.5, which means contribution or constraint from the circle and from the diamond is the same. And then what do you get? And this is a geometric view in a two-dimensional case. So this is the diamond, right? This is from the L1 constraint. And the circle is from L2 constraint. And elastic net in this naive half-half version, it's really just this slightly more oval shape, but not totally oval. And this is the constraint elastic net added. And again, you can understand this through our previous understanding. The good point is, so every point has to be within this red shape, right? That's just the requirement. And at the same time, you try to minimize, I should write beta. This is the beta least square solution. And I'm trying to, assuming I move from here, and then hopefully here, and here, and I can't go out. I can't go out this red. Every point needs to satisfy within this red oval shape. Similar as before, it's just the shape got slightly different from the L1 and L2. Question about this?
Can you go back a slide? I think I got confused with the notation.
Alpha? Yeah, I understand. Yeah, so alpha just lambda 2 over.
That's not, sorry, that was my question. I'm just wondering if the absolute value bars that they're supposed to denote more.
This one?
In that L equation, like we have plus lambda 1, absolute value 1, is that supposed to be L1 1 at the end?
Oh, this?
Yeah.
Oh, this, your question about L1 norm?
Is that supposed to denote the L1 1?
Yeah, it is. So this is this format. The L1 is the summation of absolute values of each entries.
So we're switching from the double parallel bars to the absolute value bars.
Good question. Yeah, I should have. So yes, they are the same. Yeah. So there are slight differences actually on the matrices or versus the vectors, the 2 bar or and 1 bar. But there's a lot of conventions. For the vector case, the 2 bar or the 1 bar is the same. But if that's a matrix, there's a slightly different variation of the definitions. But for the vector, see, our case is vector, they are the same. Yeah. All right. Okay, so we have the summation, and then we got really just a hybrid of the norm. Okay, so now I'm going to give you an example how people use elastic net. And this is example very, very kind of computer science flavor. So this is a paper from 2010 about predicting the revenue of a movie based on movie review and metadata of a movie. So the story in short is we're trying to use just the metadata and the review data to predict how much money a movie earns in the opening weekend. And this paper actually, the majority of the paper is more like feature engineering and analysis about what feature is related to the revenue of a movie. There are many different kinds of features, which is in the next page, but this is about the data. So they're in 2010, so to collecting this revenue, and it's just from this research group. They collected about 1,700 movies. If you think about it, this is our size N, right? So we have about 2,000 samples labeled, and you actually know their revenues, and you know you're just trying to design the features. So this is the results, but let me show you the features first. So this group of researchers designed a lot of features, like n-gram features. Hopefully, you learned about NLP or text analysis before. N-gram is really just, let's call that K-gram. K continuous words. K continuous words in the review, in whatever piece of text, those are your features. You can count the frequencies of those unique patterns and use it as your features. And if you think about it, this is a lot of features, right? Because English text, the vocabulary, just the most common size of the vocabulary is about 30,000. And then we're going to n-gram, like 2 gram, like good, not good is actually a unique pattern, right? And the combination of all the vocabulary word, of course not all, but frequent 2 grams is a lot. And you also have some other part of speech features, or there's a lot of linguistic guided feature generation. There's also all the metadata generation. In summary, we get about more than 3,000 features. So this is a classic setting, P larger than N. Question about this? About more than 3,000 features, but we have only about 200 label samples. And the reason why the researchers can be curious about this is what they want to understand, what feature or what type of properties of a movie make them earn more, right? So this is more like the more like the reason why they do this. So they give you this explanation, actually this is beta. This is what the elastic net learned, the beta vector. The beta vector, and then I think it, you can actually tell those one in 0, which means almost no influence of the features. And you can also convert those features into $1 a month just by, because that's predicting the output dollar, right? And on the left side, your right side is those features. If you have it, if the keyword, if you have it, they're get a lot of money, which you can tell, like whatever, Will Smith at that time. And then all those kind of funny words, but they are the good dollar indicator. And on your left, you can tell like documentary, the time, and philosophical, straightforward, or like whatever rated R, and those are negative features indicating actually like they're negatively related to the dollars a movie might earn. So this is a very good explanation, right? Why do I need this type of prediction models? And this is a simple, very simple formulation. Use elastic net. Hopefully in the future, but maybe those Hollywood can think about how they're going to put metadata in their movies, and then by kind of influence the open weeks, their revenue incomes. So this is what you want to get, that the researchers get out from the analysis. And let's see more concretely what's the model. The model is extremely simple, just like we just reviewed. It's slightly different from the naive version because they have a little bit weighting on the 1/2 of the L2 norm here. And in the naive version, we just have 1 minus alpha and alpha. And we don't have this kind of 1/2 down weighting of the L2 norm. So you can actually tell roughly this trying to get a little bit more sparse. So the sparsity is the more preference prior I try to enforce on the prediction I want to learn. So this is the model. Question about this?
Why does it need to be small?
Because to be more interpretable, right? If you think about it, you have 3,000 features, and how could you even making sense with 3,000 weights? You have to have ability to kind of select features, and also hopefully a small set of features. Because for a human, just to manually look at it, 3,000 is still a big number. All right, so more concretely, let's see how the researchers analyze it. This is a manual analysis, and by manually, they're actually the grad students manually group the non-zero features into groups, into categorization of the features. And then they're trying to analyze what are the weights, are the weights learned correlated well with our domain knowledge of the priors. So for example, so we always think about like sentiment-related text features should be very good features to predict the revenue, right? Because those are sentiment related features. Hopefully they indicating if the users will like the movie or not like the movie, and then that like or not like will be converted into dollars. So there's this logic story behind, right? But unfortunately from this data, those type of text features are not that important. And rather, the metadata actually a lot more influential compared to the text data. If you are a Hollywood movie maker, think about how you're going to use the story here. So this is to show you a very concrete example how the regression model can be used and how people used it before to hopefully understand a phenomenon and understand hopefully causal reasons why some got more money, some got less money. Of course, this is not causal analysis. All the regression-based analysis are correlation-based analysis. All right, so another point I want to make is, so this paper also gives you something you have not learned. It's about how to evaluate regression models. So in the homework, we always use mean, sum of squared error, but this paper actually used something kind of different. The first mean metric they use is mean absolute values, mean absolute errors. So rather than taking the square root of the error on each test samples, they just use the absolute values and then take a sum over all the test samples, then mean divided by the number of samples. And yeah, of course, this is one way to show. And the reason why the differences of absolute value errors versus the squared errors, who can give me a speculated answer? Why? What's the differences from sum of absolute error versus sum of squared error? And another metric they use, something called Pearson correlation, which you might already learn in your statistical class. So who can just maybe make a guess?
The mean square error, sometimes when the error is a little bit large, so it squares the error, so it becomes even more larger. And for like small one, it might become like more small.
Yes, that's exactly the point. The mean squared error, the issue is if you have a very noisy sample, because the square operation, it pushes the error to be really, the influence of that noise sample, the influence on the whole is actually relatively large compared to the mean absolute error. All right, so the Pearson correlation, I'm going to explain later, but this is the equation. Essentially, so this is the Pearson correlation. Hopefully you learned it in your probability 1 or statistic 1. So this is the equation. I'm not going to repeat it. What you're going to, in the regression case, you're going to calculate that Pearson correlation of the predicted y versus the true y. And there's a few other slides I'm going to show you. The y Pearson correlation, it's a good measure because it's actually bounded. So Pearson correlation is bounded from -1 to 1. But mean sum of squared error or mean absolute error, you actually might have like really, really smaller values or really, really large values. So there's no clear range of that metric. Questions about this? So Pearson correlation is a pretty frequently used metric to evaluate regression models. All right. Okay, so a little bit more about elastic net. So in my actual slides, I derived the whole thing why the elastic net can select more than n features. The main trick is elastic net equivalent to lasso. It's equivalent to lasso on a revised data, which is from the original data n times p. You actually revise it, augment with something, and which it's actually very easy into a format. It's n plus p times p, and this actually guarantees you can select more than n features just because of the size now. It sounds too much, but I don't want to spend my time and this is really for advanced students. And so I already talked about it. So the naive elastic net has the ability to select features. And in summary, so if you are not very satisfied, I'm going to go really quickly about the actual content, because just a quick review, maybe I know it's highly likely you're not going to read it if there's no quiz about it, but these are good contents. So we actually covered about how to optimize lasso. The most important in the actual slides, and also so to begin is I actually proved how do you prove ridge regression that format it can be inverted from the ending decomposition perspective. So last time I proved it from positive definite matrix perspective. But if you think about how to invert it, in the end you need to show it can be inverted, right? The most straightforward proof can be it should be based on the ending decomposition base. It's a little bit more complicated, and feel free to read by yourself. And then we actually covered about why the lasso type of error can give you sparse solutions. A little bit more intuitive is when your lambda is small enough, and this can pushes the loss function actually large enough. It can push the loss function to have this type of corner shape. And then feel free to read it, and that's related to why corner points is more easy to touch is the solution. And then I actually have a lot of derivations about how do you optimize the lasso solutions. And the fundamental idea there is direction, it's actually subgradient based, gradient descent, subgradient based coordinate descent, and feel free to read it. And because this is just too much. I used to cover this, but then later I realized it's too much for a master level of course. Yeah. So there's a whole proof, if you can read this step by step, and you will understand why. It's a very clean proof, actually. And what you are going to get is, so the reason why I give you sparse solutions is because of this soft thread holding step. And that lambda is really controlled here. If, based on all those derivations, one of the important quantity you learn, if the absolute values is smaller than lambda, you're going to push it to be 0. That's how the beta solutions, the beta vectors, a lot of the beta got pushed into 0 entries. All right, so this is there's also state-of-the-art solution called least angle regression, which we're not going to cover, but there's a more intuitive figure. And at the last is about elastic net, which I covered. How do you connect elastic net and the lasso? So essentially what you need to do in an elastic net is you rechange your formulation into y is y0 and x is x augmented by P times P matrix and scaled by a scalar, which is the square root lambda 2. And this is by reformulating your x and y into this formulation, this lasso, the solution of lasso is exactly elastic net. And I have a whole proof to show that. I think I have a whole proof to connect. Yeah, there's a lot of things actually. Oh, where's my whole proof? Yeah, I think it's this. Yes, so there's a whole proof to show by just data augmentation and the elastic net, the lasso version on the augmented data give you exactly the elastic net formulation. So all these confusions you have, hopefully you can solve those from the actual slides. And there are also a lot of very intensive, math-intensive notes related to this. Okay. All right, questions? I know this is unsatisfactory because I skipped over too many things, but they're so equation intensive. I just want to give you, hopefully, kind of track some of you to read the extra slides. Encourage some of you to read extra slides. All right. This sounds intimidating, but it's actually, if you spend some time read those, they're pretty accessible. But it just needs you to take time. All right, so let's just now summarize. What do we learn? What have we learned in the regression with regularization so far? So we have the basic model, ordinal Lister square solution, and the lasso solution, and the ridge regression solution, and of course you have the elastic net solution, which we just covered. All this formulation share the same formula. Error on the data plus regularization. So in the end, if you summarize this whole category of approach is to revise the loss function by adding regularization constraints. And we can go back to our mental representation, and I actually should put it to here. Yeah, so actually here, so we are changing the scoring function in this category, and also, of course, it revises the regression coefficients learned. It's not the beta ordinal regression solution anymore. They are shrinked version of the beta least square solutions. And of course, I mean, not just with one of L1 or L2, you can have the Q norms, right? You actually can have all the variations, like we showed before, Q equal to 4, Q equal to 0.5, Q equal to 0.1. So again, this is the contour map, right? This is the contour map of the norm function. Whoever in those blue regions share the same norm, Q norm, which is in this case 0.1 norm. So what we had used so far, it's all here. The reason is this one smaller than 1, the norm function is not convex formulation anymore, which is extremely undesired properties people used to think, because when it's non-convex, right, it's very difficult to actually optimize to guarantee the convergence properties. So in the end, actually all the regularized version is using the norm here, larger than 1. And yeah. Questions about this? All right, so yeah, so there's even, you can even go even more, right? So 2, 3, 6 inf. And when it reaches inf, the contour map changes from the oval shape into a square. And if you think about it, and what is that? So this actually means this is the inf norm, right? Inf norm means the max. 1, so when we have x2 larger than x1, we have all this output of the norm as the x2. When we have x1 larger than x2, we have all the output as, so this is the boundary point. And you can actually tell this properties of inf norm versus other Q norms. And sure.
Well, according to this means which of these following Q is the best one?
So let me repeat the question. Sometimes I might forget to repeat student question. Please remind me, because this is one of the really great suggestions from the students, which I really like. So the question is, when you have so many Q, which one do you pick? So honestly, people mostly just use 1 and 2. The reason is it's extremely difficult to calculate the gradient for other Qs. Yeah, similar to our SSE, right? Why do we use sum of squared error? And we can use sum of absolute error, right? Which we just criticized the sum of squared error, the issues. It's so sensitive to the noise, but it's such a good, easy scoring function to take gradient. So you have to consider the feasibility, right? Is it easy to take gradient of that loss function? There are actually a lot of other forms too.
Isn't it more like domain dependent? Like if we have a lot of features and we only want the important features, so we can go towards the one few. And if we want like a collection of features, we can go towards two.
Yeah, let me repeat the question is, so okay, so we have L2 and L1, and now which one to pick? So to be honest, the L1 norm is a very, very popular regularization in a lot of applications, just because of that sparse solution. But again, even though it's good, but it still have that drawbacks, right? When you have correlated features, you pick one of those features. So people have a lot of variations on the L1 norm. So the elastic net is one of the solution, but because of the solution of elastic net, because you make the data matrix much bigger, so we actually, the whole elastic net solution is the n plus p times p, right? It's still computationally it's actually good. It's a very good solution. ElastiNet is very popular. So this is one people use ElastiNet solution, and because it can select features and also kind of robust. There's another kind of solution is those called like a group norm. So rather than, because there's an issue of ElastiNet is you can't add prior there. So assuming I know a group of weights, they should be similar just by prior. In ElastiNet, you can't. It's automatically adding the group effects, right? But for a lot of applications, actually no, I know that group of features, they should have similar weights, or I want them to have similar weights. And how do you add those priors? And that's exactly how people revise a group type of L1 norm. A group norm, group 2 norm, group 1 norm. It can forces all the group weights to be similar. Either select all the groups or not select all elements in the groups. And also user predefine the group. So that's the other solution. I hope they give a good answer for your question. Yeah. So group type of L1 norm provide a strategy to add priors, human domain experts priors. Questions, ElastiNet versus other group type of L1 norm. All right, so sure.
How is ElasticNet different than Q equals to 1.5, or are the same?
Because ElasticNet, like I told you just then, right? ElasticNet is just to really just augment your data into this form. Let me repeat it. So from the original x n times p, you augment it into x n times p. Sorry. And matrix, it's a diagonal matrix I with p times p, and this is your x, your y, original y, and augmented with all the zeros, and then you just apply lasso. Because lasso has a lot of good, fast solver, and ElasticNet is really just a reformulation. It has good properties, so that's why it's a good solution. And there are many good, faster solvers for the lasso. For example, the Lars, I just quickly skipped, and they're good solvers. You don't want to have, it's kind of relatively difficult to, Question, I think I did not totally answer your question. The 1.5, right? You think about, so there's a question is, what's the differences of Q equals to 1.5 versus ElasticNet? I think there's this alpha, the lambda 2, lambda 1, and the alpha, or the lambda 2 over lambda 1 plus lambda 1, that alpha you can control. It's a much more flexible version than the Q equals 1.5. Because you can control, do you want to have more grouping effect, or do you want to have more sparse effect? Just exactly like the application we showed. In the application, they add a 0.5 weight on the L2, and hoping to add more like a sparse preference from the formulation. All right. So again, why you do this, right? I mean, this generalized well because we have less number of features. Why less number of features is good? And it's actually related to something very fundamental called Bayes and variance trade-off. When you have fewer features, you're reducing the variance. So I will talk about it later when we talk about Bayes and variance trade-off. So in the end, fewer features, p to p prime smaller than p, it reduces the variance. reduce the model variance. And of course, computationally scalable and efficient, we already talked about it, right? In the operational phase, you really don't need to save, you just save P prime, and like the memory cost or disk cost, and test, especially during the operational phase. It's both memory more efficient and computationally more fast. Of course, when you have less features, it's much easier to understand the model, exactly like what we just showed in the application, how those researchers trying to explain how the money are made, or correlated to the features, to the n-gram features, or to the meta features. All right, so this is now the last topic about how to pick regularization parameter. So this is related to the model selection. It's a very important topic and related topics to what we had about cross-validation to pick which basis function to use. In the homework 2, which hopefully I can get it out by today, you will need to use implement cross-validation to pick what polynomial term you're going to use to fit the data we shared to you. So do you do cubic or power of 5, and it's a model selection task. And in the regularization models, what we meant, model selection, in the end, it's about selecting the lambda. The lambda is also model selection. Okay, so again, so why this is even related to model selection? There's a reason behind. So first of all, then L2 type of, so why do we need regularization? Why shrinked parameter is better? Why shrinked weight vectors is better? So in the end, hopefully this kind of give you some intuitive reason. There also, of course, you can prove those theoretical way to prove it, but this is more like a intuitive reason. In general, we don't want to have huge weights, because huge weights means a slight perturbation on that feature will cause really big differences of the output. And yeah, so that's, and we prefer to have fewer features and more regular features. So we don't want to have features, because in these type of like sum of weighted X kind of models, if you think about it, you can make one weight really, really large positively if there are two features very correlated or almost the same. And how would you, if you have no regularization, assuming we have beta 1, x1, plus beta 2, x2, and I actually know x1 and x2 are highly correlated, then let me just make it extreme. x1 equals to x2, it's highly likely beta, as long as beta 1 and beta 2 equals to 0, and any model could work, right? And I can make the beta 1 super large positively, and beta 2 super small negatively. And this model still work. But this is such a bad model, right? So regularization really trying to remove this kind of situations. And I want my weights to be regular. It's in the end, it's assumption. It's the human assumption added on the model. So it's related to generalization, right? And when we talk about generalization, we have to understand what are bad generalization. There are two cases of bad generalization, which the first case is underfitting, the other case called overfitting. in the end, underfitting means the model is just too simple. It can't fit data. Both the training error and the test error are really large. And for the overfitting case is, the model is just too complex. The training error can be perfectly pushed to almost 0, but the test error is super large. And the model just, in the end, fit the noise in the training data. Let's see the cases. So you can tell roughly this is the assumption rate. This has big, kind of relative large training error, right? And this has smaller training error, but there are still training error. And this has no training error at all. And this is a pretty intuitive way to show you the underfitting and overfitting, and hopefully this is good. And of course, we talk about how to select it. We use cross-validation to select. And then for the regularization case, if you think about it, regularization is also assumption, right? In the end, regularization trying to reduce the overfitting. The regularization trying to reduce the overfitting by adding the bias. The bias is I prefer smaller weights. That's all it added. It's an assumption. In the case, let's see, I think I have L2. So I think it's maybe here. So, sorry, I should actually put this page back in the after. If you think about L2 and L1 are adding two different biases. And L2 penalized larger weights more, and L1 penalized small weights more. They have two different biases added to avoid overfitting. Question about this? Yeah, they have. If you think about, there's really two type of bias or two type of strategy to avoid overfitting. All right, and apparently, this is a good case for L2, right? Yeah, that's exactly the grouping effects, which L1 cannot do well for this problem, for this setting, but L2 can do very well. All right, so we covered overfitting, and then regularization is about avoiding the overfitting, penalize the overfitting. L2 and L1 penalize in a different way. Yeah, sure.
So how would you decide if you would rather go with a smaller polynomial or regularization?
Good question. So in the end, we have so many tools learned, right? They're polynomial, they're local RBF, kernel functions, basis function. There's also this regularization. So if you think about basis function, they are trying to avoid underfitting because they are giving flexibility to the model. And the regularization is trying to avoid overfitting. These are actually from two different directions. One, basis function give more flexibility to the model. Regularization reduced flexibility of the model. Let's actually see how do the regularization control. So again, it's about control the bias and variance of the model, which I have not even covered. What do you even mean bias or variance, right? So we're going to cover next Wednesday about the definition of this, but it's good just you understand it now, just roughly get it now. So there's a very important concept in the regularized model called regularization path. So it's actually very easy. It just, you have different lambda, you plot. So in this problem, it's just a problem with only 8 features. This data has only 8 features, so that's why I have 8 different beta. beta 1, beta 2, beta 3, beta 4, beta 5, beta 6, beta 7, and beta 8. And for different lambda, because we said, right, when lambda is kind of really, really large, and all the beta will be small, will be 0. If you remember that circle, when beta is super large, your circle is super, super tiny, close to the origin point, which just means every vector, every weight will be 0. And you just plot it for different lambda by decreasing the lambda to close to 0, and you plot the learned beta. This is called regularization path. You see how the different beta changes. And it's a very interesting figure to show what data, what feature maybe influence more to the prediction. And you can actually tell very clearly this feature is relatively important, no matter how much regularization you added. And you can see other paths like this feature, when the regularization gets more, and it's the influence becomes the smaller positive into the negative. And the whole path tells you more a trajectory of the influence of the features to the prediction output. So, and yeah, this I graded, and then I hope you understand. The last version is your without a regularization, right? This the last point. Each is one solution, corresponds to one beta. This is beta 0. This is exactly ordinal least square solution. Question about this? It's a little bit hard for the first peak. And what we actually learn in the end is vertically the vector, that's your vector. Every point here together builds up a specific beta vector to that corresponding beta sub whatever beta you have, lambda you used there. And you really just draw it. And then by connecting the whole path, you see how the feature influence when your lambda changes. You can do the same thing for the lasso. And the lasso, this is called a regularization path, right? Because we said the lasso is a feature selection, has a feature selection functionality, which is very clear from the regularization path. Because when you have a large lambda, gradually in the beginning there's no feature selected, and gradually only this feature got selected. Its weight also got improved, like increased a little bit more. Then until this point, this lambda, there are 2 features got selected, and then even a little bit more, there are 3 features got selected, until the end, when your lambda is 0, all the features got selected. And this also gives you a full spectrum about importance of the feature when the lambda changes. But again, in the end, you still have to pick a lambda for the operational model, right? This helps you understand the full spectrum, full trajectory of how feature changes when you have more and more prior of regularization. And you still have to pick a lambda through cross-validation. Hopefully that's this point, which give you the lowest cross-validation error. But in the regularized model, people normally not just see only one lambda corresponding beta, they see the whole path, because the whole path tells you the whole trajectory of the performance of the features, right? And again, the lambda, that type of prior, is what you added. That's my bias added on the model. Question about this, and then again you can do the same thing for lasso. Hopefully this is the best lambda you pick, and for this lambda, you actually pick 1, 2, 3, 4, like 4 features, or actually 3 features. In this case, only 3 features. This is the best lambda star through cross-validation. You pick this lambda, and all the other features are still 0 at that point. All right, so actually this is all about everything I want to cover. And we are finalizing the whole supervised regression section. We did not cover Newton's method, and we did not cover locally weighted linear regression and k-nearest neighbor-based regression, but this is not required at all. After we talk about k-nearest neighbor, it's very intuitive, it can be understood. And Newton method, it's a good optimization method, good to learn, but it's